So we're going to go ahead and continue with our lecture here. So we're looking at our first definition for 2.2. Officially, we already looked at concave up and concave down using that demonstration on Desmos. Here's the definition for concave up and concave down. And so making sure you're familiar with the language here. So again, here's that picture of concave up, concave down. You can see some things. F is concave up over some values or interval, what we call. If F prime is increasing over the interval, F prime. So we're looking at the derivative. So this is the original function. If the derivative is increasing, F is concave up. If the derivative is decreasing, so even though it's positive, it's getting the slope of the line is getting is decreasing. Here you can see it would be increasing over time, and so if that is happening, then we know that. So we'll be using those definitions to determine again if a function is concave up or concave down. We'll also be looking for some other things. And so the second derivative test, or the test for concavity, is right here as we look at that there. It's similar to what we did for 2.1, our first derivative test. If the second derivative is greater than 0, then the graph of f is concave up. If the second derivative is less than 0 on an interval, then the graph is concave down. So we have that connection there between those values. Concave up and concave down is connected to second derivative. And so what we have is this connection between, we have a connection between concavity of a function and its second derivative. So we have that connection there. And again, as this makes sense, if the second derivative is positive, that means the first derivative is increasing. If the first derivative is decreasing, right, that means f is turning down, or we have a, if the first derivative is decreasing, then the second derivative is going to be negative. And so we have those connections there. Then that leads us to, again, so you make sure we'll talk about that. And then that leads us to theorem 5, which is actually the test. And so go ahead and take a look at that real quick as you read before I discuss. And so the second derivative test for relative extrema, again, an extrema mean max or min, right? Could be either one, max or min. Suppose f is differentiable for every x in an open interval. So again, the function has a derivative, and that there is a critical value. So just like we found in 2.1, for which f prime of c equals 0, then this is our conclusion here. We know we have a relative minimum if the second derivative is greater than 0, a maximum if the second derivative is less than 0, because again, that's showing us our concavity. And so from our introduction, there's our concavity right there. This is concave down. And so we have this is concave down here, second derivative. And then we have this view here, looking at this here. And so we have that connection between where you would have a maximum and a minimum. And then it depends on the concavity. So you see how this is concave up, it holds water. We have a minimum, second derivative greater than 0. Here, the concave down, right? It's concave down. This is concave up. And you have a minimum. You have a maximum when it's concave up. Minimum when it's concave. A maximum when it's concave down, which is second derivative is negative. A minimum when the concave up, which is the second derivative, is positive. For f double prime of c, the first derivative test can be used to determine whether we have a relative min or max, which we learned in 2.1. So here's an example real quick. Graph the function. There it is. What we're going to now do with the second derivative test is take the first derivative and the second derivative, And then from there, what we like to do is we're going to set each of those equal to 0. So when you set the first derivative equal to 0, you get your critical values. Again, you can look at the algebra. We then set the second derivative. We use the second derivative also. We're interested in where the values of the second derivative. And so in this case here, we first find the value. So once we had these critical values here, -3 and -1, what we're going to do is we're going to substitute those values in here into the second derivative. Because what's going to happen is once we now know these are critical values, these could be max or min points, right? Because we now know these are potential max or min points, -3, -1. We know from here if we know it's a minimum if the second derivative is greater than 0, a maximum if the second derivative is less than 0 at those critical values. And so that's why they get substituted in there. And then you have, this is negative, so then -3 is going to be a maximum. At 1, since it was greater than 0, it's a minimum. That goes back to, again, our second derivative, theorem 5, or the second derivative test for Extrema. And so that's what we have. And then, of course, you can find the actual points by plugging a -3 and 1 into F. And that gives you those actual points. Okay, and then from there, we would use Desmos. You can kind of hand sketch that. We know where the points are, but then Desmos would help us then actually graph the complete graph. But you should be able to verify when you plug when you plug this in here, you should be able to verify the algebra and calculus we've done there. Okay, so that's example 1.